So let's drill deeper now on a crucial aspect of transporting hydrogen on board, namely refueling. In our next 3 technology pitches, we will look more carefully at this very crucial issue. And we begin with a joint presentation by Toyota and Hyundai on refueling with gaseous hydrogen. And ladies and gentlemen, we will take questions after these dual talks. Please note in general to which speaker your question is addressed, but I must say as a caveat, in the case of the coming presentation, we cannot take questions for Jung-Ki Kim because in fact we are using a pre-taped presentation for him. So you can certainly submit questions for our first speaker in this next pitch, and he is Vincent Mattelaer, fuel cell specialist at Toyota Motor Europe. He will get us started and then we'll move on to our presentation from Hyundai. Please, Vincent, the floor is yours.
Good morning, United States. Good afternoon, Europe, and good night, Asia. So my name is indeed Vincent Mattelaer, senior engineer working at R&D Toyota Motor Europe, fuel cell powertrain division. So I will tell you this presentation is actually split into 3 parts. You have first 10 minutes talking about the Toyota approach for heavy-duty fueling. Then I will change my cap and will deliver a 10-minute presentation concerning PRHYDE project. And then the last 10 minutes is for Hyundai, who will talk about total cost of ownership comparison between 35 megapascal and 70 megapascal gaseous hydrogen fueling. So it is my pleasure to talk to you about the viewpoint of Toyota towards heavy-duty vehicles and more specifically towards heavy-duty refueling. Next slide, please. So here you see the slide of actually the overall strategy. And I have to tell you that Toyota heavy-duty vehicles is not considered as a separate item within our portfolio of fuel cell application. It is really an important integral part of the overall Toyota strategy. So in our holistic vision, when you want to move towards a complete overall hydrogen mobile society, you cannot look at heavy-duty fuel cell vehicles alone without taking the passenger cars into consideration. Also, fuel cell technologies, the manufacturing of those parts, and the industrial use need to be taken into account. You could even go further and even look at the total hydrogen society where storage of hydrogen and so on is also included. There are actually all of them linked together. So it is true that commercial vehicles will increase hydrogen consumption for sure, but the fuel cell components of these trucks cannot be mass produced in hundreds of thousands of units immediately. And therefore, we need also the passenger vehicles in our vision, because those vehicles will be produced in a very high number. And the components of these vehicles will be produced really as very high mass production. So by sharing the components such as fuel cell stacks and tanks, receptacles, and so on, between the passenger car vehicles and the commercial vehicles and even industrial use applications, we can reduce those costs. And we can make actually the trucks cheaper. Next slide, please. So as we are using these shared components, let's look at the trucking itself. And for us, because we are using these shared components, we actually opt for 70 megapascal compressed hydrogen fueling. Because our targets for passenger cars were already to achieve over 500 kilometer range, so long range, very short fueling times, 3 minutes. And we also have only limited space for fitting the tanks at an acceptable price. So for us, actually, it was only logic and evident that we would use 70 megapascal compressed hydrogen. Liquid hydrogen for passenger cars was absolutely not within our vision. So sharing these parts evidently means that we also believe for heavy-duty trucks that they will also initially use gaseous hydrogen at 70 megapascals. I have to tell you, at Toyota, we do not oppose towards liquid hydrogen or cryogenic compressed hydrogen at all. We think it could be interesting to use on the long term for heavy duty fueling, but we believe that it will be initially gaseous hydrogen at 70 megapascal. That will be the trend for the heavy duty transportation. As you can see on this slide, we have already projects running at this moment in United States and in Japan, and the customers in these two countries are different. So we need to provide a solution to our customers. And all the fuel cell trucks that are shown on this slide that we are producing together with our partners, they will all be equipped with 70 megapascal Type 4 tanks. And the fuel capacity range is, it starts at around 7.5 kilograms for the very small, medium-sized duty vehicles, such as the 711 trucks, up to very high capacities in the Class A trucks. Currently, you can see 60 kilograms, but capacities up to 100 kilograms. I think that should be possible in these vehicles. And obviously, they should be fueled in a fast and convenient way in order to reach diesel parity. Next slide, please. So we need to fuel fast in order to reach diesel parity. Now, when we are looking at the H70, so 70 megapascal fueling hardware, we have this already available. There is a H70 nozzle available up to 60 grams per second. And we even have already kind of heavy duty protocols that are existing in the JPEG standard or the SAE D-type protocol. But those are more for light and medium duty trucks. So up to, let's say, about 30 kilograms of fuel. This is suitable. You can fuel within less than 15 minutes. But for some of our customers, this will be for sure too long fueling, or for others, it's not enough, such as the Project Portal that uses 60 kilograms of fuel. And for those, there is in the United States, they are already using just a dual H70 nozzle approach. So in that case, they are able to fuel already today up to 60 kilograms within 15 minutes time. But even that will not suffice. So we need to go even further, and then we need to develop new hardware. And Toyota at this moment is in the progress of working on the development of two different types of new technologies to reach this objective. So in Japan, at Toyota Japan, we are working on the mid-flow nozzle and the mid-flow receptacle that can be implemented in current stations with only minor adjustments to be made. The costs will not be very high, and the mid-flow nozzle is actually also a kind of normal upgrade of the current H70 nozzle. It's so not extreme new development. So Toyota is at this moment evaluating to implement the mid-flow receptacle into all our next generation vehicles, passenger car, the medium duty and heavy duty applications. With this mid-flow nozzle set up as in a dual nozzle mode, we are able to fuel up to 100 kilograms within 15 minutes, or even 50 kilograms within 10 minutes. So that should be possible. In the United States, my colleagues over there, they have decided that the the capacity even needs to improve and the fueling times need to be improved to reach diesel parity. So there we are also working on the development of a high flow nozzle that is able to fuel 100 kilograms within 10 minutes. And this is with a single nozzle design that is able to fuel at these high speeds. Next slide, please. So the development of this nozzle receptacle, but also other parts like the hose and the breakaway coupling, that is done in the United States industry group, where Toyota works together with Shell, Air Liquide, Nel, Nikola, and Hyundai. And so this will, at the end of this year, actually the first prototypes will be finished and an experimental work should have been performed. And the results of this project, of this joint industry group, will be forwarded to the ISO, and they can be used for the development of an update of the ISO 17268. But the new hardware is obviously not enough. We also need new software, a new protocol. And new protocol will need to be developed to reach these high fueling objectives. And for this, Toyota is also a member of the PRHYDE project. I will cover this in detail in the next presentation. But I can already tell you that the outcome of this project will also be shared with the ISO, so they can use this information to develop a standard, a new refueling standard, the ISO 19885. Next slide, please. So here is shown an example that dual nozzle fueling is already existing. So heavy duty trucking is not the future, it is the current situation, because in Los Angeles, they are already in the port, they're already fueling these trucks. These trucks are driving every day in the port. And there are 5 stations currently available that are using this dual nozzle design, 2 from Air Liquide and 3 from Shell. So it is already happening as we speak. And all of them actually are also using the SAE J2601 2020, the Type D protocol. Next slide, please. So a question I get very often in that case is, yes, but how about the compatibility between these different receptacles and nozzles? Well, the advantage of using the mid-flow receptacle is that it is still compatible, fully compatible with H35 and H70 stations, nozzle designs. So it could be beneficial for some customers when they have, for example, a medium duty truck, that they are able to fuel the truck also at the H70 passenger car station. As for the high flow fueling, that one is intended only for the real big heavy duty trucks with very high capacity, and it would not be so beneficial to have them fueling at low capacity stations. And therefore, these heavy duty vehicles can only be fueled at high capacity stations. Next slide, please. We are also collaborating with the ISO to develop new standards. So there is a brand new working group, 24, that is working on ISO 19885, which did not exist yet. So they have already started the work in March 2021. And this is divided into 3 separate parts. The first one is about how to design and the development process of the fueling protocol. The second part is about the communication between vehicle and station, because obviously you will need probably some kind of advanced communication between those two in order to have very high flow fueling. And the third part is the protocol itself, where we will also provide input concerning medium flow and heavy flow protocols. Then the other working group 5, an existing one led by Nicola, that will be the update of the ISO 17268, where also receptacles will be introduced concerning mid-flow and high flow. And this work will start next month. Next slide, please. So thank you very much. And I will change now my cap and change the presentation to another one for the PRHYDE project. So the PRHYDE project is called Protocol for Heavy Duty Hydrogen Refueling. Next slide. So let's have a look at the objective. So the objective is written here on this slide to investigate compressed gaseous hydrogen. So it's not about liquid hydrogen, only compressed gaseous hydrogen. To investigate refueling protocol requirements to help facilitate future standardization of fueling protocols for medium and heavy duty vehicles. But I must say this is actually not really limited to only medium and heavy duty vehicles. It could go further, such as ships or trains or other applications that need high capacity tanks. They could also benefit from the outcome of this project. Next slide. So why do we have the PRHYDE project? Because I just explained you that we do already have a protocol available at the SAE and the JPEG for more than 10 kilograms. Well, in order to fuel heavy-duty vehicles with high-capacity tanks, they are actually a bit limited. So we do have those new D tables, but the flow is limited to 60 grams per second. And although they are certainly a solution for some of the medium-duty truck applications, they're really too limited for heavy-duty fueling. These protocols also consider the fueling station to take the full responsibility. And as the fueling station takes the full responsibility of the fueling, the protocol is not really optimized on vehicle data, such as the different tank types, the pressure drop values, even station specifications are not taken into consideration. So this leads to the most conservative values to be taken for each component in the fueling process, and therefore to quite lower performance. For those who are in the refueling industry, they already know quite well that SAE fueling according to the SAE protocol is very safe, but it is a bit limited. These protocols are also very prescriptive. So it provides almost no flexibility for the station supplier if they want to increase the performance of their station. So they have to stay always within the prescriptive conditions of the SAE. There is the -2 of the SAE J2601, but this is actually only the boundary conditions, and it does not include any information what is needed to develop a heavy-duty protocol. So therefore, a new modern approach was really necessary to achieve heavy-duty fueling targets. So let's have a look at the approach of the PRHYDE group. Next slide. So it starts with still a classical approach, which means that it is still divided into 3 pressure classes, 35, 50, and 70 megapascal. But that's still classical. But then we go into a deeper concept. So there were several concepts made, 7 in total. And this was done by working group 3 of PRHYDE. They went quite far, and they formulated 7 different fueling concepts based on the level of detail, such as the info from the CHSS or the hydrogen tank. The possibilities are that there is either no info at all or extremely limited, like in the current SAE protocol. Static info, so which is, for example, sent just before the fueling, or the info could even be dynamic during the fueling itself. The station on the control itself, it could be done by the station, fully 100% by the station, like it is done right now, or it could even maybe be done by the vehicle who commands the fueling, similar like with the battery electric vehicles who are connected to a charging pole. Or it can be a shared responsibility between the station and the vehicle. And the description of the protocol concept could be extremely prescriptive, where it is very well written what you need to do exactly, or it can be a performance-based protocol where the station really has much more flexibility to improve the fueling itself. So all of these were taken into consideration. So we come to 7 because there is just one which I grayed out. The condition without any tank information is not considered within PRHYDE. Obviously, if you look at the right side, the dynamic or vehicle control or performance-based, there the current infrared communication will not do, and we will probably need a new communication standard between the vehicle and the station. Now, I must tell you that this communication standard is not part of the PRHYDE project. Next slide, please. So the current state of work package 3, who is developing the protocol itself, is that they have now 7 fueling concepts that are all based on an improved MC formula method. And one of the concepts has even fills controlled by the vehicle. The current state is that the performance comparison of the fueling concepts have started, and it is currently investigated how much they are better than the existing protocol. So this is done at this moment. And an important remark is that although most of the fueling concepts are intended to be used with more advanced communication, some of the concept can be used with existing technology. So it should be technically perfectly be able to be integrated into current existing stations and using infrared communication. Next slide. So these are the current conclusions of work package 3, that the proposed fueling concepts are all anticipated to improve the performance in comparison to the published standard protocol, category D. And at the same time, it is also a wish from the PRHYDE partners that the final fueling protocol shall be adaptable to station and vehicle designs that consider costs and performance also that take that into consideration. Next slide. But protocol development is not enough. We should, of course, validate these protocols, and this will be done in work package 4 and 5, where we have the simulations and the experimental validations. So for concerning the simulations, we have gathered all the detailed data of 3 different tanks, one from Nikola, one from Toyota, one from NPROXX, and CFD meshing has started for these tanks. And both Air Liquide and NG have their own CFD methods or CFD simulations. These have already been benchmarked, so they came to very similar conclusions. So very soon they will start with the modeling of these protocols. As soon as they receive from work package 5 the first experimental data during some single tank fuelings. Next slide, please. So in work package 5, there were several single tanks. We will start with single tanks. Afterwards, we will do full truck fueling simulations. But the single tanks, they are equipped with instrumentation such as thermocouple trees and strain measurements and so on. So they can do this testing and measurements, which can then be implemented into the CFD model. First results are to be expected mid-May. Next slide. So here is the outcome of the PRHYDE project. So the outcome of the PRHYDE project, what you will see at the end of this year is not a 300-page booklet like the SAE standard is currently. It's not really a standard. It is really the draft fueling protocol description methodologies, what you need to do, what kind of considerations, next steps, and it will also include flow charts. But it is all proof of concept that has been tested and validated, so that you can trust. And it will also include a lot of recommendations for station manufacturers and OEMs, such as for fueling concepts or safety implications. Next slide. All our reports, most of them are public, and you can download them on www.pryde.eu. If you need more information, you can always send an email to info@pryde.eu. Next slide. So, and this is a project that has received funding from the FCHJU too. So thank you, Bart Bieberg, for this. And it is a joint undertaking that receives support from the European Union's Horizon 2020 Research and Innovation Program, Hydrogen Europe and Hydrogen Europe Research. Thank you very much. And I will leave now the word to Mr. Kim.